everybody. Just to make sure that everything is in order. If you can hear my voice and see my screen, please type yes in the chat box. Okay, all right, so everything looks fine. Okay, thank you very much. Thank you very much. So this is where we stop. Oh, come on. Next time, I will wear my Star Wars T-shirt. But not today. Maybe next time. Don't distract. Say, I'll be all over the place. I need to focus here. I need to deliver. I need to deliver a good class today. See, today I have a bad feeling about this. Really, I really do. I have a bad feeling about this. Oh well. Where was I? Okay, so today is a very important class. Okay, you need to bear with me. If you only want to learn one topic, this root locus interpretation is the one that I suggest. You're going to earn a lot of marks by learning how to draw this root locus diagram and make interpretation of it. You're going to be asked twice. The only topic that is going to be asked that you are sure that you are going to be asked twice in this course is this root locus interpretation. Once you're going to be asked in your test, which you are going to earn 10 marks out of it. And the second time is going to be asked again in your final. You're going to earn another 10 marks. See, you are going to earn 20 marks out of what we are going to talk about today. See, it is that important. We cannot be distracted with anything else today. I'm trying. I know I'm trying. Okay. I hope that motivate you enough to pay attention to this. Okay, that is out of the way. This is where we left off the last time. See example 3.11 here. Use the magnitude and angle criteria to verify that a point -1 plus j is one of the roots of the characteristic equation of the control system shown below when k is equal to 4. So let us recap what we have done. What is this root locus anyway, and what is the characteristic equation, so that it can make some sense to us. Of course, we can go through the mathematics and then prove that this is the roots of the characteristic equation using this magnitude and angle criteria. But let us recap what we have done before. Okay, so when we have a closed loop system here, consider this closed loop system with a proportional controller K and a system to be controlled G and a feedback gain H. See, the characteristic equation is defined as 1 plus kgh equals 0. So this is the denominator of the overall transfer function. Denominator of the overall transfer function. It is called the characteristic equation for a reason. This characteristic equation, this equation will determine how the system is going to behave. It is called a characteristic equation for a reason, 1 plus kgh. And kgh on its own is known as the open loop transfer function. 1 plus kgh is the denominator of the overall transfer function. See, you need to make you need to distinguish between the overall transfer function and the open loop transfer function. So KGH on its own is known as the open loop transfer function. But root locus diagram is here, is written in blue here. The root locus is the path taken by all roots when they are traced out in the complex plane when the parameter k is varied from 0 to infinity. See, when k is equal to root locus tell us the location of all roots on the complex plane when k is varied from 0 to infinity. Why is that important? We are going to talk about the usage of root locus diagram after we learn how to draw the root locus diagram. We're going to delay that discussion. So here, KGH on its own is known as the open loop transfer function. Now let's go back to the question. See the question here. This is for k is equal to 4. We want to verify that a point on the complex plane, a point S1 with -1 plus j is one of the roots when k is equal to 4. In fact, this is just one of the point on the root locus. So k will be varied from 0 to infinity. K is equal to 4 is just one of the point. But all points on the root locus must satisfy the angle and criteria, the angle and magnitude criteria. I have my mouse today, and my mouse is working properly. See? Every point on the locus must satisfy the magnitude and angle criteria. The magnitude criteria says that the magnitude of KGH must be equal to 1. Of course, this is obvious from the characteristic equation. See, 1 plus KGH, you bring 1 to the right-hand side, and then you have KGH equal -1. The magnitude of -1 is 1, and the angle of -1 is plus and minus 180. Right? So the angle must be the angle of open loop transfer function. If the point is one of the roots, the angle must be plus and minus 180, and the magnitude must be equal to 1. So let's go back to the question here. So the question here wants us to show that using the magnitude and angle criteria, that this point is one of the roots. All you have to do is substitute this value in the open loop transfer function, and then to see whether the magnitude is 1 and the angle is 180. It is as simple as that. So I don't have to write a lot today, so my note is already self-explanatory. Okay, let's go to the final example. Okay, here. Okay, so using the magnitude and angle criteria, we want to show that a point -1 plus j is one of the roots. So when k is equal to 4, so your first task is to obtain the open loop transfer function. The open loop transfer function is KGH. So KGH is just, since our h is equal to 1, so KGH is just equal to k divided by s squared plus 4s plus 6. So this is the open loop transfer function. But here we are given that k is equal to 4. We want to see when k is equal to 4 is this is one of the roots. All you have to do is substitute the value of k, substitute s, and then see whether the magnitude is 1 or the angle is 180. So now k is equal to 4, substitute k is equal to 4, substitute s using this point -1 and j. So you substitute, this is s squared, 4 multiplied by s, 6, and then you simplify that, you get that expression. So the magnitude is given by 4 is a real number. The magnitude of 4 is already 4. So -1 plus j is a complex number. The magnitude of that is square root of the real part square plus the imaginary part square. So square root of -1 square plus 1 square. And the magnitude of 2 plus 2j is the square root of the summation of the square of the real part and the imaginary part. So this is just a Pythagoras theorem. And then now you can see that, so the magnitude is equal to 1. So this is one of the criteria that the point on the on the root locus must satisfy. So the first one is already satisfied, magnitude is equal to 1. And the second part is the angle of this expression, the angle of this expression. So you have the numerator is equal to 4. So the angle of 4 is just 0. 4 is just a real number, is 0. And then we have the denominator. So that is why you have a minus sign there, because when the term is in the denominator, you put a minus sign and you use the arctangent of the imaginary part divided by the real part. And then you have the second term here. So minus here is because the term is in the denominator. Again, you use the triangle, the real part divided by the imaginary part, and then you just sum it up all together. So you get the angle is negative 180. So therefore you satisfy both criteria. And then therefore we can conclude that the point negative 1 plus j is one of the roots of the system. Why it is one of the root? Because this is a third order system. So for third order system, you're going to have 3 roots for a particular value of k. But this is just one of them. Okay, so but we are not going to go through all this tedious argument and computation when we want to draw the root locus diagram. There is it has been developed. The root locus diagram, the drawing of root locus diagram procedure has been established. All we have to do is just follow how we can draw accurately the root locus diagram. See, the root locus procedure has been outlined here. I know it is a lot. Okay, you look here. It is listed the root locus procedure: 1, 2, 3, 4, 5, 6, 7, 8, 9. I know it's a lot. I completely understand that, but there's no way around this. There's no way around this. You need to embrace this root locus, this 9-step of drawing of root locus. You need to embrace this. You're going to earn 20 marks from this alone. 10 marks from your test, and then another 10 marks from your from your final. I'm not going to read one by one. We will come back to this. I'm just going to explain this using an example. Okay. The first thing we need to do is we need to clear the term here. See, poles and zeros. These zeros will cause a lot of trouble, especially when you just hear me talking without having a face-to-face interaction. It's going to sound the same. Zeros and the numerical value of 0 sound just the same. So let us clear things out about the terminology that we are going to use. Okay, so okay, I'm done with this. Okay, so let's open our new notes today. Okay, so I have uploaded this new notes to your e-learning. This is already week 7. Week 7. We are halfway through. Okay, just open that. Okay, so this is already in your e-learning. We need to clear things up here. The terminology that we are going to use. Okay, so 1 plus kgh is called the characteristic equation. Kgh on its own is known as the open loop transfer function. So when we are drawing the root locus diagram, the root locus diagram that we are going to draw is the root locus diagram of the closed loop system. See, 1 plus kgh is the characteristic equation of the closed loop system. we are just using the open loop transfer function to help us draw the root locus diagram of the closed loop system. See, there's a confusion there already. One is a closed loop system, one is the open loop transfer function. Let me say that again. What we are drawing, yeah, I had a bad feeling about this. I know. What we are going to be drawing is the root locus diagram of the closed loop system. Make no mistake about it. But we are using the open loop transfer function kgh to help us draw the closed loop root locus diagram, because 1 plus kgh is the characteristic equation of the closed loop system. But 1 is just a constant. So all we have to do is pay attention to the open loop transfer function, and then we can draw the root locus diagram. 1 is just a constant. It has no bearing on the root locus diagram. It's just a constant. All right, so there's another terminology that we need to clarify here. See, the open loop transfer function kgh can be written in a form of factor. The numerator can be factored out and the denominator can be factored out. So this is known as the zero pole format. So when you write the open loop transfer function in this format, so this is known as the zero pole. What are the zeros? What are the poles? So zeros is the name given to the value of s that will make the numerator equal numerical value 0. See, I want to distinguish between numerical 0 and the name given to that value. So Z1, Z2, Z3 are known as 0. Their numerical values not necessarily equal to the value of 0, but the name given to that is called the zeros. So from now on, I will make a distinction. When I say 0, I mean this Z1, Z2, Z3, so 0. So numerical 0, I will say the origin. When I say the origin, meaning that the origin of the complex plane. Sometimes I say 0 for that as well. But I will try to make sure that when I say 0, it means that the value of this Z1, Z2, Z3. So when I say poles, is the value of P1, P2, and P3. Those are the poles. All right. Any question? Is that clear? I know it is a lot. Don't worry too much. Don't worry too much about this. We'll get this. Okay. So now, when we want to draw the locus diagram, all we have to do is follow the 9-step outline in the notes. This 9 outline. See, the first step is locate the poles and 0 of the open loop transfer function and plot them using X and O's. So that's the first step. You need to identify the poles and zeros of the open loop transfer function. Then the root locus on the real axis lies in the section of the real axis to the left of an odd number zeros and poles and 0. So the loci begin at the pole and end at zeros. If there is not enough 0, then the loci will end at infinity along asymptote. I'm just going to talk about this 1, 2, 3 first. Okay, so let us look at an example. I'm going to skip example 12. We are going to go straight to example 13. Okay, draw the root locus for a control system with open loop transfer function given as below. So this is already open loop transfer function. Now I'm going to go to my whiteboard. Okay, so we are given this open loop transfer function. So draw the root locus for a control system with an open loop transfer function given as k divided by s plus 2 and s plus 4. It is already written in zero pole format. Now let's go to our 9th step of drawing the root locus diagram. Okay, so the first step here says that locate the pole and zero of the open loop transfer function. Okay, so there's no zero. So this is our open loop transfer function. There's no zeros. There are two poles. Poles at -2 and -4. Okay, so there you have it. There's no zeros because you don't have s in the numerator. You can only have k, and you have poles. You have two poles at -2 and -4. Now let's go back to our procedure here. So then we already identified poles and zero. And then locate the pole and zero and plot them using x for poles and o for zero. We need to plot that. Locate the poles and zeros and plot them using x for pole and o for zero. Since we don't have any zero, so we don't have to plot for zero. We only have to plot for poles. We have two poles, one at -2, one at -4. Okay, so you put x there at -2 and -4. So now, so we are done with this first step. Locate the poles and zero of the open loop transfer function and plot them using x and o for zeros. O for x for pole, o for zero. That's the first step. The second step, root locus on the real axis, we are talking about on the real axis, lies in the section of the real axis to the left of odd number of poles and zero. Now we are talking about on the real axis only. So this is the real axis. On the real axis, the root locus exists to the left of odd number poles and zero. So you start from the right. So there's the first pole, which is odd number pole. So there is the second pole, which is the even. On the real axis, locus only exists to the left of the odd number poles and zero. So to the left of -2, you're going to have the locus. To the left of 4, you don't have a locus because this is already even. Let's read that again. The root locus on the real axis. We are just talking about on the real axis. On the real axis, root locus lies in the section of the real axis to the left of odd number poles and zero. So this is the first one, which is odd. So to the left of that, we're going to have a locus. So this is even. The second pole, it is even. To the left of that, we have no root locus there. So we know that in this region, you're going to have a root locus. So I'm going to draw with a red line. Okay, so by rule number 2 here, so we can identify that on the real axis, that section is going to have our locus. Okay, so that's the second step. There's nothing to it. See, everything is clear. Nothing to it. There's nothing to worry. Don't worry about it. Okay, now let's go to the third guideline here. The loci begin at the poles and end at zeros, or zeros at infinity, along asymptote. Since in this example we don't have any zeros, so therefore when you have two poles, you're going to have two locus, because the locus is going to start at the pole and it's going to finish at zeros. But since we don't have zeros, so we're going to have, so our locus is going to end at infinity along asymptote. Somehow our locus is going to branch out and then end at infinity. The loci begin at the pole. See, the loci begin at the pole and end at 0. If we don't have zeros, then it's going to end at infinity along asymptote. So meaning that here, the locus start at the pole going from -2 is going to the left, from -4 is going to the right, and finally it's going to branch out and go to infinity. See, the locus is going to start at -2 and go to the left. And another locus start at -4 and go to the right. And somewhere it's going to branch out and go to infinity, because we don't have zeros. We don't have any zeros. Okay, let's go to our fourth. So since we say that our locus is going to end at infinity, so we along asymptote we need to find the asymptote lines. So the number of asymptote is equal to the number of pole minus the number of zeros. So in our case, we don't have any zero, so we have p is equal to 2. The number of pole is equal to 2. Therefore, we're going to have 2 asymptote. And then the asymptote angle can be computed using that expression, 2r plus 1 multiplied by 180 divided by p minus z. In this case, since we're going to have 2 asymptote, so we're going to use r equals 0 and r equal to 1. Let me go back to my okay. All right, so the number of asymptote is equal to the number of poles. We have 2 poles, and the number of zeros, we have no zeros. P is the number of pole, Z is the number of zero. So we have 2 poles minus no zero. So we need to find 2 asymptote line. So the asymptote angle, sigma A, asymptote angle can be computed using the expression given in the guideline. 2r plus 1 multiplied by 180 p minus divided by p minus z. Okay. So use r equals 0 when r is equal to 0, so 180 divided by 2. When r is equal to 1, you get this is the angle in degrees. So this is the angle that our asymptote line is going to follow. But where does it intersect? So we can compute another value here. The intersection of asymptote. All asymptote intersect the real axis at a single point. So this is called the intersection of asymptote. We can use this formula. So the intersection of asymptote happens at the summation of pole minus summation of z, summation of pi minus zi divided by p minus z. Pi is the value of the individual value of the poles. Zi is the individual value of the zeros. P is the number of poles, Z is the number of zeros. So we can use that formula. So the Pi is the value of individual poles, so -2, -4. We don't have any zeros, so minus nothing there. So the number of pole minus the number of zero, so we have no zeros. So this is going to be our intersection of asymptote, which is going to be equal to -3. Okay. So now we know that our asymptote is going to go through -3. So this is line -3. So this is sigma A here, -3. And one of the angle is 90. So I'm going to draw the first asymptote line. The first asymptote line goes through -3 at an angle of 90 degrees. So that is our first asymptote line. So this is 90 degrees. Second asymptote line going through the same intersection, but at an angle of -270. So it's not negative, it is positive 270. The second asymptote line is going to go through the same -3 and then at an angle of 270. So it's going down. So there you have your two asymptote line. Okay, and we know that finally our root locus is going to approach that asymptote line. Okay, so we are done with this. 1, 2, 3, 4, 5. And then at what point will our locus break away? That's going to approach the asymptote line. So we need to compute where the point the locus is going to branch out from the real axis. So the breakaway point can be computed using the sixth guideline here. So points of breakaway from or arrival at the real axis may also exist. In this case, we have that point. We can compute that by writing the characteristic equation. Rewrite characteristic equation as k as a function of s, and differentiate that with respect to s equals 0, and then we can get the breakaway point. Okay, now we are going to compute the breakaway point. See, I'm running out of space to compute the breakaway point, so I'm going to erase this. I'm going to erase this this computation of asymptote. Okay, so we need to rewrite the characteristic equation as k is equal some function of s, and then we need to differentiate that function. Okay, so now we now obtain the breakaway point. It so happened that the breakaway point is -3, coincide with the point, the intersection of asymptote. So we know that this is the breakaway point, -3, and then we can come here and finish our drawing. So this is -3, one branch going up and one branch is going down to infinity along an asymptote line. So that is our complete root locus diagram. Just -3. Okay, so that is how you get your root locus diagram. I know it's a lot to swallow now, but after we have drawn a few of them, then it's going to be a second nature to us. Okay, so let us take a break here and come back and we'll try another one. Okay, so let's come back at 4. This is 4, right? This is 4, 40. Let's come back at 5 and continue our discussion from there. Let's take a break.